Hey everybody, today we're going to be talking about derivatives of complex valued functions. And here's our first definition. Suppose that W equals f of z is defined for all values of z in the immediate vicinity of the point v0. So we can draw a circle around the point z0, and our function f of z is defined for all values of z in that circle. Then the derivative of f at the point z0 is denoted f prime of z0, and it's given by the limit as z approaches z0 of f of z minus f of z0 over z minus z0. And this is somewhat comparable to one of the definitions of the derivative of a real valued function. F prime of x naught is the limit as x approaches x naught of f of x minus f of x naught all over x minus x naught. And in the context of a real valued function, this is the slope of the tangent line, y2 minus y1 over x2 minus x1. So this definition of the derivative of a complex valued function is just the complex number analog of the derivative of a real valued function f of x. Now, probably we didn't see this definition much when we were doing calculus, the calculus of real variables. Instead, we probably saw this definition or something like it. Let delta z equal z minus z naught. Then the derivative of f evaluated at z naught is the derivative of is the limit as delta z goes to 0 of f of z naught plus delta z minus f of z naught all over delta z. The real valued function analog of this would be delta x goes to 0, f of x plus delta x minus f of x all over delta x. So when we were doing calculus, this is probably what we saw most often. Now we can write this in dy dx notation, or in this case, dw dz. Remember that w and f of z are the same thing. So if we let delta w be y2, which is f of z naught plus delta z, minus y1, f of z naught, then the derivative can be written this way. The limit as delta z goes to 0 of delta w over delta z, and we denote that dw dz. I'll give you a second to look at that before we put these definitions to work. Well, I guess there was one more thing I wanted to do before I went to some examples, since we're talking about notation. In complex analysis, we use the analog of the differential operator d dx. The symbol d dz is an instruction that tells us to compute the derivative of the expression that follows. So given this entire expression, the symbol the expression d dz tells us to compute the derivative with respect to z of the expression that follows. So here the symbol d, dz, tells us to compute the derivative of the function f of z. Now let me add one more remark to this. Also, having to do with the d, dz notation, we regard the entire expression, that is, this entire expression, d, dz, f of z, we regard this entire expression as being the derivative of f evaluated at z. So, this whole expression is the same as f prime of z. So d dz f of z, that whole expression, same thing to us as f prime of z. Okay, now we'll do some exercises. Okay, let's compute the derivative of a function using this definition of derivative. And the function that we have in mind is f of z equals z cubed. So we'll use the definition f prime of z naught equals the limit as z approaches z naught of f of z minus f of z naught over z minus z naught. And let's say limit as z approaches z naught. F of z is z cubed. F of z naught is z naught cubed over z minus z naught. And as usual, if we try to plug this thing in, if we try to compute this thing by just plugging in z naught for z, we're going to get z naught cubed minus z naught cubed over z naught minus z naught. We're going to get 0 over 0. But the good news is, since we get 0 in numerator and denominator, we know there's a common factor that we can cancel out. And here's the key. When we plug z sub naught into this polynomial, we get 0. And that means that z minus z naught is a factor. Now, do I know how to factor the difference of cubes? Yeah, I guess I do. Especially since I know what one of the factors is. One of the factors is z minus z naught. And let's see, I got to have a z squared here. Z squared times z will give me my z cubed. And whatever goes here has to be such that when I multiply it by negative z naught, I get negative z naught cubed. So I guess z naught squared will go here. Z naught squared times negative z naught cubed looks good. And let's see now. I have z naught times z squared negative z naught times z squared. So it looks like I'm going to need a positive z naught times z squared. So let's see. Apparently the middle term is the product of both of these. Z naught. Let's see if that works. See, I have negative z naught times z squared, but I don't have that here. So somehow I've got to get rid of that. Let's see. Z times z naught times z is positive z naught times z squared. Okay, that looks like it's going to work. And in general, this is how we factor the difference of cubes. This sign, I'll tell you what, I'll write that down after I finish this exercise. I'll write down the factorization of sum or difference of perfect cubes. Oh, there's our troublemaking factor. And we cancel it out. We cancel out top and bottom. And so that leaves us with limit as z goes to z naught of z squared plus z naught plus z naught squared. And let me see, can I compute this limit by plugging in the number that z is approaching? I'd like to do that. I'd like to plug z naught in for z, and that would give me z naught squared plus z naught times z naught plus z naught squared, which equals 3z naught squared. But the only question is, what gives me the right to plug z naught in for z when I compute the limit of this function? And it has to do with continuity. This function in the variable z and the constant z naught, it's a polynomial in the variable z. And we know that all polynomials are continuous. And if polynomials are continuous, then we can compute the limit of a polynomial by plugging in the value that z approaches. And see, that's essentially a characteristic of a continuous function. So first of all, let me diagram that and give an explanation. I'll say by continuity of this polynomial, z squared plus z naught squared plus z naught squared. It's a polynomial. We get to plug in the value that z approaches in order to compute this limit. Now let's see, why can we compute a limit by plugging in the value that it approaches if the function is continuous? Well, if x is continuous, then the limit as z approaches z naught of f of z is equal to f evaluated at z naught. This is the definition of continuous, that continuous at the point z naught. That in order to compute the limit of this function, we can plug in the value that z is approaching. So this is essentially the definition of continuous at a point z naught. So the consequence is we can compute the limit of a continuous function by plugging in the value that z approaches, which is what we did. And now let's see. Let me just encapsulate our final results. That's what we figured out. And let me write it using my DDZ notation also. Z naught can be any value of Z. So apparently what we proved was that this holds true for all values of Z. So in general, the derivative of Z cubed is 3Z squared, which doesn't surprise us, but it's kind of reassuring because essentially it's telling us that for the most part, the derivatives that we know from calculus carry over into real analysis. Now, let's try this a different way. Let's do the same thing all over again. We'll just use one of the other definitions to do this. Oh, don't let me forget, I still have to write down the factorization formulas for the sum and difference of perfect cubes. I think I better let this blackboard writer die a death with dignity. Okay, we bring in a replacement. So f of z naught plus delta z, that's going to be z naught plus delta z cubed minus f of z naught cubed, all over delta z. And we cube this. So we get the first thing cubed plus 3 times the first squared times the second plus 3 times the first times the second squared plus the second cubed. And everything that doesn't have a factor of delta z will remain. So we have 3z naught squared delta z plus 3z naught delta z squared plus delta z cubed over delta z. And every term in numerator and denominator has a factor of delta z, so we cancel those out. Now, how do we evaluate this limit as delta z goes to 0? Well, now z naught is the constant, but delta z is the variable. And we have a polynomial in the variable delta z, which means we can plug in 0 for delta z. That's because a polynomial is a continuous function. Okay. So we get the derivative again, 3z naught squared. Okay, a word of caution here. Some caution should be exercised when we compute the derivative using the limit process. And we'll have an example here. Show that the function f of z equals z conjugate is not differentiable at the point z naught equals the origin. So at the point z naught equals the origin, apparently this derivative does not exist. Let's see how we're going to do this. Whoops, force of habit. It will use this definition of the derivative. And given z naught equals the origin, let's see what this boils down to. F prime of 0 equals the limit as z approaches 0 of f of z minus 0 minus f of 0 over z minus 0. And that's the limit as z goes to 0. Let's see, what is f? F is z conjugate. So, Z minus 0 conjugate minus 0 conjugate all over Z minus 0. So this is the limit as Z approaches 0 of Z conjugate divided by Z. And I'll let you look at that for a second. I'm going to erase the board just to give me some more writing room. So this is the derivative that we're computing. F prime of 0 is the limit of this function as c goes to 0. And from the work that we did with limits in the last lecture, if we want to show that the limit doesn't exist, then we pick two different paths for z to approach z naught. And we're very strategic in picking those paths. We pick two different paths for z to approach 0 such that we'll get different values each time. So let's be strategic, but let's try to keep it simple too. If z approaches 0 along the positive x-axis, then z is just equal to x, isn't it? On the positive y-axis, on the positive x-axis, y is 0. So this limit becomes the limit as x goes to 0 and z conjugate, we change the sign of the imaginary part, right? But if y is 0, there is no imaginary part, so this is just x. And if y is 0, z is just x. So this is the limit of 1, which equals 1. So our candidate for the limit of z conjugate over z as z approaches 0 along the positive x-axis is 1. If this limit exists, then we have to get the same result as z approaches 0 along every other path. So let's try another simple but strategically selected route of approach. If z approaches 0 along the path, let's see, let's go for the positive y-axis. Then our limit works out this way, z conjugate over z And this becomes, let's see, if we're on the positive y-axis, then x is 0, isn't it? And so z conjugate is just negative iy, and z conjugate is positive iy. So we have the limit as z goes to 0 of negative 1, which equals negative 1. Oops. Yeah, the value of this expression is dependent on the path along which z approaches 0. Hence, this limit doesn't exist, but this limit is supposed to be the derivative of f evaluated at z0. And maybe I should just write what that is. Derivative of f evaluated at 0. So the derivative itself doesn't exist. So especially in complex valued functions, if we compute the derivative by the definition, we have to exercise some caution. It's not like real valued functions where x can approach 0 from the right or x can approach 0 from the left. Let's see. X approach 0 from the left and x approach 0 from the right, and those are the only two choices. In the xy plane, as z goes to z0, there are infinitely many choices. So we have to be careful when we compute the derivative by the definition. When we studied calculus, just in order to keep us from having to compute the derivative by definition, we made a list of rules and properties for derivatives. And the same rules and properties of derivatives that we had in calculus have analogs in complex analysis. It's still true that the derivative of a complex constant is 0. The power rule for a complex variable raised to a power still holds. Same power rule. The derivative of a constant times a function is still the constant times the derivative of the function. The derivative of the sum or difference of functions is still the sum or difference of the derivatives of the functions, which means that when we compute the derivative of the sum or difference of functions, we compute the derivatives term by term. Compute the derivative of the first term, compute the derivative of the second term, and so on, and then just add or subtract them. There's a product rule for real valued functions. The same product rule for complex valued functions holds. You may not have seen this version. Whatever version you know from calculus is equivalent to this, and you can use the version from calculus that you know if you still remember it, and hopefully you do. The quotient rule, essentially the same quotient rule that we had in calculus, derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. In calculus, there's a chain rule for the derivative of a composite function, derivative of the outer function evaluated at the inner, times derivative of the inner function. And then finally, a special case of the chain rule, the derivative of a function raised to a power. Well, the outer function is raising something to the n power. So this is the derivative of the outer function, n times something to the n minus 1. And it's evaluated at the inner function, and we multiply by the derivative of the inner. Or if you want, you can just do this and say power rule as usual. Times the derivative of the inner function. Bottom line, all of the derivative rules that we know from calculus essentially hold in complex analysis. Now there's a result from calculus, a classic result, that also holds in complex analysis. And essentially that result is this. If a function is differentiable, in other words, if its derivative exists, then that function is also continuous. Let's take a look at that. Here's our classic theorem. F of z is differentiable, or if f of z is differentiable at z naught, then f of z is continuous at z naught. So differentiability implies continuity. Now another way of saying this is that if f prime of z naught exists, then the limit of f of z as z goes to z naught is equal to f of z naught. And this is not difficult to prove, believe it or not, so let's do it. So I guess the first thing that we want to do is recall the definition of continuous at a point. F of z is continuous at the point z naught exactly when limit of f of z equals f evaluated at z naught. So f of z is continuous at the point z naught exactly when the limit of f of z as z approaches z naught equals f of z naught. Another thing that I'm going to refer to here the limit is z approaches z naught of f of z naught. What do you think this should turn out to be? Well, remember what f evaluated at z naught is. Z naught is a constant, so this is f evaluated at a constant, which means this is the limit of a constant, so we're going to get what? The constant, right? F of z naught. And then finally, we have this definition of continuity. The limit is z approaches z naught of f of z equals f of z naught. And I just want to get an equivalent form for this. So this is true if and only if the limit as z approaches z naught of f of z is equal to the limit as z approaches z naught of f of z naught. So what did I change from here to here? I replaced f of z naught with the limit of f of z naught, which is fine because we can do this. F of z naught is a constant, so the limit of f of z naught is just the constant. Now what do I want to do? I think I want to say that this is true exactly when, and I'm going to subtract this thing from both sides. Limit as z goes to z naught of f of z minus limit as z goes to z naught of f of z naught equals 0. And right here I have the difference of two limits. Well, didn't we learn that the limit of a sum or difference is the sum or difference of the limits? That goes the other way too. The sum or difference of limits will be the limit of the sum or difference. So that means that we have the limit of f of z minus f of z naught equals 0. So let's see, what did I really establish there? I started here and I started there. So let me write down what I really established. I established that this thing is the same as that thing. Our criterion for continuity, the limit as z approaches z naught of f of z equals f of z naught. This criterion is exactly the same as this criterion. That is the limit as z goes to z naught of f of z minus f of z naught equals 0. These two things are the same. So we got our preliminaries out of the way. And what we're going to prove is if the derivative f prime of z naught exists, then the limit of f of z equals f of z naught. It's only necessary to show that if f is differentiable at z0, then this thing is true, because this means that the function is continuous at z0. So we'll take as true the hypothesis that f prime is differentiable at z0. That is, f prime of z0 exists. And now we're going to take this expression and show that it's equal to 0. We just multiply top and bottom by z minus z0. Z minus z0 is just 1. We haven't changed anything. And now we have the limit. And you know what? I guess I better write it this way. Yeah, I'm taking f of z minus z0 and multiplying it by z minus z0, dividing it by z minus z0. And we have the limit of this expression. And we know that the limit of a quotient is the quotient of the limits. The limit of a product is the product of the limits. So essentially, we can do this. So I guess what I want to do here, now that I think about it, is I will look at this thing as being a product. It'll be the product of this times that. And so I'll get the limit of the first thing times the limit of the second thing. But what is this whole limit? Isn't that f prime of z0, which does exist, doesn't it? And this thing is going to be equal to 0. This is a polynomial, so we can plug in z0 for z, and we get 0. Okay, we proved what we had to prove. Namely, that if we suppose that f prime evaluated at z0 exists, in other words, f is differentiable at z0, then the limit as z approaches z0 of f of z minus f of z0 is 0. And we might wonder really where the fact that f is differentiable at z0 comes into play. Yeah, we took this thing and we said, yeah, this is the derivative f prime. And so we have f prime times 0, that's 0. But why is it such a big thing that f is differentiable? We'll see if f is not differentiable, it may be because this thing, the derivative, is going to positive infinity. And then we'll have a limit of the form positive infinity times 0, which is not necessarily 0. Or this expression could be going to negative infinity. And we're looking at negative infinity times 0, which is not necessarily 0. But the fact that this expression exists and it's a real number means that the limit will be a real number times 0, therefore 0. So essentially we proved what we had to prove was that this limit equals 0, given that f is differentiable at z0. So even for complex valued functions, if a function is differentiable, it's also continuous. Now I do want to I want to do an example or two, but before I do, I need to do L'Hopital's rule, which holds for complex valued functions. And here's the statement of the theorem. Suppose that f of z and g of z are differentiable, and that f evaluated at z0 and g evaluated at z0 are 0. Now, what is this really saying? Well, if these functions are differentiable, they're continuous, right? And so if this thing is 0 and this thing is 0, what does that really mean? It means that as z approaches z0 of f of z, we get 0. Or by continuity, we get f evaluated at z0, which is 0. And since g is differentiable, the limit as z goes to z0 of g of z is equal to g evaluated at z0 because it's continuous. But we're told that g evaluated at z0 is 0. So our hypotheses are really telling us that when we compute the limit of f of z over g of z as z approaches z0, we're going to get 0 over 0. So that's really the situation that they're telling us. As z goes to z0, f of z over g of z looks like 0 over 0. Now, the conclusion of the theorem is that given this scenario, we can compute the limit of f of z over g of z by computing the limit of f prime of z over g prime of z. Now let's see why that works. So we'll let the hypotheses be given. And we have the limit as z approaches z0 of f of z over g of z. But what this looks like it looks like 0 over 0. So that's no good. So here's what we do. we take the numerator and the denominator and we multiply top and bottom by the same thing, which is, you know what? I got to do something else first. Silly me. F of z naught is 0. So I can just add that here, can't I? After all, it is 0. And g of z naught is 0, so I can throw that in here. Haven't changed anything, have I? I'm just subtracting 0 from the top and subtracting 0 from the bottom. I haven't changed anything other than the appearance. Okay. Now I have f of z minus f of z naught over g of z minus g of z naught. And what I propose is that I multiply top and bottom by 1 over z naught. I'm sorry, 1 over z minus z naught. And I'm just multiplying by 1 here. Numerator and denominator are the same, so I haven't changed anything. So what do I have? F of z minus f of z naught over z minus z naught, and g of z minus g of z naught over z minus z naught. And I have the limit of a quotient. And that's the same as the quotient of the limits. So I can write limit as z goes to z naught of f of z minus f of z naught over z minus z naught. And all of that over the limit as z goes to z naught of g of z minus g of z naught and what's this? F prime evaluated at z naught, right? And this g prime evaluated at z naught. Now, look where we started, and look where we finished. So let's just recapitulate. Whoops, 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 whoops. Yeah, that's right. F prime of z naught over g prime of z naught. Now I want to do an example. This one might look kind of familiar. We did it yesterday, but we're going to do it a different way today. The top is a polynomial in z. The bottom is a polynomial in z, so they're continuous. which means that we can compute the limit of this quotient by just plugging in z, provided that the denominator is not 0. Well, let's see. That we try plugging in and we get 2 plus I squared minus 2 times 2 plus I plus 1 minus 2I. And did I do that right? No, 1 plus 2I here. Okay, I think I did that right. And do the bottom now. 1 minus I times z, 2 plus I, minus 3 plus I, so 2 plus I squared, we get 4. And when we square I, we get minus 1. And then we get the first times the second doubled, so that's 4I. Minus 2 times 2 is 4. Minus 2I. Plus 1 plus 2I. And up above here, I'll just write what that really is. 3 plus 4I. And on the bottom, let's see, I have 2 plus I minus 2I plus 1. And then I have minus 3 plus I. And what do I have here? This is 3 minus I. Yeah, so here's what happens. We add these up, we get 0 over 0. So if we plug z naught into the numerator, we get 0. If we plug z naught into the denominator, we get 0. So by L'Hopital's rule, this is going to be the limit as z approaches 2 plus I of the derivative of the numerator over the derivative of the denominator So let's see. Remember, this is a constant. Its derivative will be 0. So the derivative of the top is 2z minus 2. And the derivative of the bottom, this is a constant. Its derivative is 0. This is just a constant times z. So the derivative will just be the constant, 1 minus I. And we're still computing the limit as z approaches 2 plus I. So what we have here, this entire expression, is the limit as z approaches z naught of f prime of z over g prime of z. The numerator and denominator are continuous. They're polynomials. So we can just compute this limit by plugging in. So we have 2 times z, 2 plus I, minus 2. And on the bottom, it's just a constant. So we plugged in z naught for z. And what this is f prime of z naught over g prime of z naught. Okay, dividing by 1 minus I, that's the same as multiplying top and bottom by the conjugate. And so we get 1 plus 1 is 2 on the bottom. And on top we get 2 plus 2I plus 2I minus 2. So we get 4I over 2, which is 2I. Now this is the same one that we did yesterday, but today we did it using L'Hopital's rule. And that's our lecture for today. I will have homework problems coming out with this video.